Okay. Welcome everyone to the third talk on attacks and pitfalls. Today we'll first talk about an attack, a very famous attack on the well-known piece of IBM hardware called the IBM 4758. This unit is a very secure IBM hardware unit. It's actually designed as a plug-in card for PCs. But what it actually is it's a unit that has on board, in fact, a full-fledged computer. There's CPU, there's RAM, there's also a battery, which we get back to in a moment, battery support. And around this thing is a very advancedly designed physical protection layer. And the reason for this is because the unit contains also a whole bunch of cryptographic keys. And what the unit does is it provides cryptographic services, like it can encrypt data, decrypt data, and so on, do authentication. And of course, the idea is that all this happens inside the box, so your keys will be much better protected than if they had to live, outside in your probably very insecure standard PC environment. What the thing does here, what this protection does, is that because of the battery support, it's alive all the time. It keeps a constant view of what happens to the system. It measures temperature. It measures what goes on in the protective layer here. And if somebody is trying to drill a hole or do something strange to the unit, it will detect this and will immediately delete all the keys, delete everything, and become completely dysfunctional. So in this way, the idea is that you're supposed to be able to do your whatever cryptography you want to do with much better security than you would otherwise be able to have. But of course, this thing does have to talk to the outside world. So there is, of course, a way to call functions inside here via an application program interface, an API, that allows you to address certain keys and ask to have something encrypted under a certain key and get the ciphertext back, stuff like this. And so you could say this application program interface here is what kind of defines the security policy for the box, because it defines what are you allowed to do. And that, in fact, this API is, in fact, as far as anyone knows, the only way you can talk to the box. As far as I know, nobody knows how to break into this physical protection without, as I said, the box noticing this and simply deleting all the data inside. So the API here, on the other hand, is a pretty complicated thing. I've seen the manual once. It's a 100-page document. So it's pretty complicated what this whole set of functions that are available. And of course, therefore, such a security policy, being such a complicated beast, it becomes quite complicated to decide what does this thing actually allow. So if somebody gets access to this API and starts calling all these functions in some sequence, what could that result in? That's a pretty complicated question to answer. And indeed, it turns out that can be seen as the Achilles heel of this thing, that it has a pretty complicated API. But before we get there, I need to tell you some more background also on what the box can do. So you might remember from the confidentiality section of the course that we had this DES block cipher that we talked about, the old American encryption standard for block cipher encryption. It's not a standard anymore because it only has a 56-bit key, and that's not enough these days. But because IBM had a patent on DES for many years, there was a long time whenever you bought IBM security equipment, you could be sure that there would be DES encryption inside it. IBM, of course, also realized that the single DES is not good enough, so they designed a better version, which is called 2-key triple DES or 3 DES, where the idea is that instead of having a single DES key of 56 bits, you would use 2 keys, K1 and K2. So this would be 112 bits total, and this would be much better, of course. And what it does, basically, so just to define what it does, so 3 DES encryption on the 2 keys K1 and K2 of some message block M would be the following. So first you do DES encryption under the first key of the message. Then you do a decryption. So I write this as des inverse under the second key of this thing. And finally, you do a des encryption on the K1, the first key again, on the result of this. So it's triple des. There are 3 operations here, and there are two keys, as you can see. So you might wonder why the decryption in the middle here. And indeed, from a security point of view, there's no reason why you couldn't just do 3 encryptions. However, the reason for the decryption there is because somebody thought it was a great idea that if you wanted to be backwards compatible with older equipment that only knows about single key DES, what you can do is that you can choose K1 to be equal to K2. So if you do this, then of course, 2 of these operations will cancel out because it's encryption and decryption, and you'll be left with just a single encryption, right? So that means that if you have a newer system that can do this 3-des thing, it can also talk to older equipment. So that would seem like a nice practical idea from a usability point of view. But the problem is that now you introduce a possibility that you could have these much weaker keys, so-called replicated keys. And of course, normally, if you choose your keys randomly, as you would normally do, then of course this would not occur. But if you do this on purpose, you now have 2 levels of security inside your system. You have the replicated keys, which are much weaker, and you have ordinary keys, which are stronger. This is always potentially a dangerous thing to do because maybe the attacker is able to fool you into degrading to the lower security level. And that's always something that you should be worried about. And you will see in a moment why this problem shows up in this context. Okay, so back to the IBM 4756. So the last thing I need to tell you in terms of background here is that if you have 2 of these boxes, one way that you can make them communicate with each other is to allow one box to generate a key, say K here, and then manually transport that key to the other box here on the other side here. Because this also comes from a day and age where public key cryptography was not necessarily something that you had available. So what you can do here is that you can ask this box here that has the key first to generate 2 so-called key parts, K1 and K2, which are randomly chosen with the property that the XOR of K1 and K2 is the key that you're interested in. Then what you do is that you let this first box output these 2 key parts to 2 different users, 2 different administrators, if you will. So this guy gets K1, this guy gets K2, maybe on a chip card, maybe it's some other way. And then these 2 guys, they go to the second box, and then they input K1, respectively K2. And this, of course, allows the box now to create the XOR, and this way we can stock the original key. So the purpose of this, of course, is that if you only know K1, it's not very hard to see that this tells you absolutely nothing about K, right? Because seeing K1, from your point of view, K2 could be absolutely anything. And of course, your string XORed with something completely arbitrary can generate any result whatsoever. So as long as these 2 guys do not collude, then the key K will be secure. So of course, it does break if they collude, but this was a known risk that the designers said, well, we don't think it's likely enough that these 2 people will collude. It's too unlikely for us to worry about, so we'll take that risk. So that's of course fine, as long as you take a conscious decision that that's what you're going to do. The problem, though, is that because of this replicated keys scenario we talked about before, and because there's this key transport mechanism, there was a PhD student from Oxford University who found out that, or Cambridge University actually, who found out that by combining these things in a clever way, you could actually start doing some nasty things, and in the end steal all the keys from the box without having to collude with anyone. Now, yeah, so the last thing to say here, I don't need anything more than, is to say that one thing that is characteristic also for hardware boxes like this is that they very seldom have enough memory inside for all the keys that they have to store. So therefore, there is something called key export. So what that means is that you have a so-called key encryption key inside the box. Let's call this K. It could actually be one of these things that you transport from one box to another. But then if you have a different key, K prime here inside, and you find out you've run out of memory inside the box, and now you want to store some of these keys outside, you call a key export mechanism. And what this outputs is the encryption under the key encryption key of the K prime here. And this can now be stored in the much bigger storage outside, but of course securely, because the idea is that this key encryption key here never leaves the box. And so everything should be fine. That's what is known as key export. These key encryption keys are defined such that they're not supposed to be used for data encryption. They're only supposed to be used for this kind of exporting thing. Okay, so now finally to the attack that this guy defined. So there's a whole bunch of steps here. So one step is you generate a data key first. A data key, let's call this K prime. And this is going to be a single length key. So what that means is it's a 56-bit key, not very strong. And then you, so you have to remember that when you say generate this data key, that means this key K prime sits inside the box. You can't get to it so far. What you can do though, is that you can ask for the encryption of some message M that you can choose. And what you'll get out of this is the encryption on the K prime of this message block M. And then of course, because K prime is a single length key, you can simply brute force search and find the K prime. So this is what we do. So you brute force K prime. There is hardware available out there that can do this in a matter of hours. It's really not very hard. So now we know K prime. We were not supposed to, because it was supposed to sit inside the box, but nevertheless, that's what has happened now. And then the second step is we generate a key encryption key, which I will call K1. And this is going to be a replicated key. So key encryption keys are, double length keys. But this one, we asked this one to be replicated, so it's weaker. And then we do an export. This is also allowed. So we export under our K1, we're going to export this K prime from before. Okay, so this is allowed, right? Because K prime up here was a single length key, and K1 is also a weak key, so that's fine. You can export a weak key under a weak key, no problem. Of course, you are not allowed to export a strong key under a weak key. This would violate the conditions. But now you can see, because K1 is a replicated key, it's really only a 56-bit key. It just consists of 2 equal halves. So we can now brute force K1. Okay, so this seems like a rather convoluted way to get to a point where we can brute force K1. And by the way, yeah, we can brute force K1 because we know K prime. So now we know something. We know a plain text and we know a ciphertext under this key K1 we're trying to brute force. So this works in the usual way. The reason why we do this rather convoluted way of getting to a point where we can brute force K1 is because K1 is supposed to be a key encryption key. And you're not allowed to encrypt data that you choose yourself under a key encryption key. So therefore we go this detour. Okay. So now we know a key encryption key, K1. It is, however, a replicated key, so it's weak. so we cannot directly use that key to export all the keys of the box that we really wanted to. We can, of course, only get the weak keys. So now we do an extra trick. So we say, this is step 3. We input that was very ugly. Let's get something better. So what we do is we input a key part, K2. So now we have to remember back. So when we talked about this key transportation mechanism, what happens when a box receives a key, right, is that it receives both these key parts here. So at some point, some guy comes along and says, okay, here's a key part. And so maybe you key this in manually some other way, but you input this K2 at some point. So now the attacker pretends that that's what he's doing at this point here. So you input a key part K2, and this, very importantly, is not replicated. And so this means that now we have a situation where we have 2 key encryption keys, namely K2, that we know because we just input the thing. And we also know this K1 because we brute forced this just before. And so the final step of the attack is we combine key parts, right? So we pretend that K1 was actually a key part that's supposed to be used inside a key transportation mechanism. So we combine K1 and K2, and the box will do this. So it's going to set K to be K1 XOR K2, just like in a normal key transportation. An interesting part is that now, because K2 was not replicated, that means that K is not going to be replicated either. And therefore, the box thinks that K is a strong key. Okay. And therefore, now, as step 5, we are simply going to export all the keys we want, all the keys of the box, by encryption on the K. And this is, of course, a complete disaster for the security of the box because the attacker knows K, right? I mean, we know K2 because we just keyed this in. We know K1 because we brute forced it. So we know K, and therefore we can steal all the keys from the box. Not so good. So the take-home message here, I guess I would say that, so the take-home here from this attack is that, first of all, several security levels if you have this in your system, you should look out. You should be careful. Because the problem is that you should look out because the problem is that once you have several security levels, the attacker, you can be sure you'll get attacks that will try to fool you into degrading to the lowest security level. And that's exactly what happened here. We have, on one hand, we have replicated keys which are weak. We have non-replicated keys which are strong. But it turns out that by misusing the lower security level, mixing these things up in an unfortunate way, then things went wrong. That's one thing. And also the other thing is, I would say, beware of complicated policies. Because that's exactly what happens if you have the security policy for the box being specified in terms of an API that fills 100 pages to describe, then there is quite a big probability that you may find that what you defined as your API in fact allows something that you didn't realize that it allowed, such as, for instance, this thing. The mistake here, of course, has later been corrected, so you can no longer steal keys in this way from IBM equipment. But the point, nevertheless, is of course still valid. So that's one thing. That was the first attack for today. The second attack concerns something a little bit different, namely this business where you have attacks that are just completely out of the box. and does something that nobody expected. So to understand how this works, let's say we have a client and a server, just like we have usually in TLS SSL kind of setup. And let's say that the client wants to send a message to the server, encrypt it. Then one way you can do this is you can encrypt under a symmetric key, so message M here. Both client and server have the key, we assume. And let's say that the encryption on the key K here is actually CBC mode encryption, which you've seen before. This is blockwise encryption, where you process your message in blocks. So what you have to do is that, in fact, what you do here is that you split your message into blocks, let's say M1, M2, and so on up to MT, and then you encrypt each of these blocks with this CBC mode. What CBC mode does is not really that important for this discussion here. What is important is that this last block here, of course, blocks have to have a fixed length. It would be like 128 bits if it was AES we were talking about. So the message can have any length, so you don't know whether this last block here, MT, is actually complete. So therefore, there will be some padding applied here. So there's a certain procedure that you use to pad out the last block to a block boundary. And in some cases, you might even add an extra block to do this. And therefore, what the server would usually do here when it receives something like this is that it would do the following. It would decrypt, of course, on the K, the key, and then it would check the padding. So the idea is that the padding is supposed to follow a certain procedure. It has to have a certain form. And if that padding is not correct, then something must have gone wrong at the sender side, the server thinks. So the client needs to be told that something was wrong. So the natural thing, of course, is once you check this, you send back, either an error message or an OK message. So basically just one bit comes back saying whether, everything went fine or there was an error. In general, the server can also do more stuff here. Usually maybe the message that gets decrypted, if the padding was okay, has to be processed some more before you actually send back the message saying whether everything was okay or it wasn't. But that's something we can discuss later on. Anyway, so the thing was that for a certain, there exists a certain padding method, which together with CBC mode turns out to be problematic for security. And there was an attack on this. And basically the attack works as follows, that, so here's the adversary. And he sees a ciphertext, which is the encryption under the key that he doesn't know, of course, of some message. And then the adversary eavesdrops the ciphertext. And the attack that was found on this thing was the following, that the adversary now very cleverly from C constructs a bunch of new ciphertexts. A whole bunch of these C1 up to Cn. And all of these he will send to the server. The server, doing its job, of course, knows the key, will try to decrypt each of these things, will check the padding and so on. And therefore, for each of these ciphertexts you send, you'll get back one of these error messages. So E1, E2, up to En, each of them saying, was it okay or was there a padding error? This is just the server doing its normal job, right? But the interesting thing now is that from all these bits, so because C1 to Cn was constructed cleverly from the original C, and because the server used its key here to compute these error messages, it actually decrypted stuff, then it turns out that the adversary can now reconstruct the original message. So this, in some very convoluted way, it turns out that the server actually helped the adversary decrypt this original ciphertext. Not so good, of course. So it turns out this problematic algorithm was used, in fact, when the attack was found, it was actually used inside TLS SSL context. And And of course, people started wondering, do we now have to change this algorithm? And the first conclusion was that no, we don't, because you might remember that in TLS, it is always the case that connection in both directions is encrypted. So that means that, of course, when the server sends the server sends back to the client this error message here, this error message will be encrypted under a different key. So that would mean that the adversary will not get to see this error message. Like the original attack assumed that you could see and clear whether there was a padding error or not. But of course, if there's encryption, then the adversary doesn't get that information. And so the first conclusion was, we don't have a problem. Well, it then turns out that some French guys found out that no, this is not the case. There was still a problem. And the reason for this, yeah, maybe we can see it already in this drawing here. So let's reconsider, what is it actually that the server does here when it decrypts? So it decrypts first the ciphertext under the key K. It will uncheck the padding. And now remember, there are two possibilities. Either there's a padding error. If this happens, then of course you can immediately send back a message, there's a padding error. And then your job is done. You can go on to the next ciphertext. But if the padding is okay, there's more stuff to do. Usually you might have to process the plain text message. There's maybe some other information, maybe some MAC that has to be checked and so on. So at some point, if everything is okay, then later on you send the okay message. So you can see that the timeline here says, if there's a padding error, then in fact, you will see a message coming back fast. If there's no padding error, you'll see a message coming back later on. So what these guys therefore noticed is, well, even if we cannot see what the error message is because of the encryption, we can just measure the time it takes for the server to answer. And if it takes a short time, we'll assume there was a padding error. If it takes a longer time, there wasn't. And in this way, we learn exactly the same information that the adversary could learn without the encryption being there. They tried this out in practice, and it turns out that this actually does work as long as you are close enough to the server. So you don't have too many network hops in between you and the server. You can actually tell the difference between these two time intervals. They found that as long as they were behind something like 2 network switches and a firewall, they could still tell the difference between the shorter and the longer time. So this is a good example, I guess, of something where the attack model is incomplete. This was something that nobody had thought about at all. Just to connect this, of course, all the attacks we look at can be categorized inside these attack categories that we looked at in the beginning. So just to give you an example of this, we can maybe talk about how this attack here actually fits into the categories, just to give you an example of this. So we have stride. First of all, that was the attack goals. So this attack, of course, is, I would say, information disclosure, because you managed to decrypt some ciphertext that you were not supposed to decrypt. So you managed to steal some information here. Then, because this was a network attack, it makes sense to look at X800 because that classifies network attacks. And it's certainly an active attack because the adversary is inventing his own ciphertext that he sends along to the server. So it's modification of the normal traffic. That's one thing. And then we have the INO classification, which says who attacks us and where. So it's an external attack, clearly, because you don't have to be a user of this system. You don't have to be the client or the server. You can be an external attacker that just, comes in from wherever and does this. It's a network attack, as we just agreed. So it's not offline, it's not online. You don't have to be inside the server system at any point in time to do this attack. You can just manipulate the network traffic to do this. And finally, there's the TPM. Was it the threat model? Was it the policy? Was it the mechanisms that failed here? And I would say it's definitely the threat model, because it's a T. It basically was assumed that nothing was wrong because we have kind of made sure that the attack beat that was there before is not possible any longer because of the encryption. But it turns out, after all, it was. So that was the end of this lecture here. There's one more left on some really funky attacks that you'll see later on.